This video will cover section 5 of your Unit 7 Similarity Flipbook. It's the top flap of section number 5, and this section is labeled Triangle Proportionality. Here is our essential question. How can I use triangle proportionality to find missing measurements? And once you get that copy down, class, then let's define triangle proportionality. Here's the definition. If a segment intersects two sides of a triangle and is parallel to the third side, it divides the two sides it intersects proportionally. And it also creates similar triangles. Now pause the video, write that definition down, and then when you're done, go ahead and continue. Alright, let's continue and break this definition down. If a segment intersects two sides of a triangle, take a look at EB. EB intersects two sides of our triangle, AD and AC, and it's parallel to the third side. Let's go ahead and mark that. You've learned this on Integrative Math 1. If we want to mark that EB and ED are parallel to each other, we're going to go ahead and make a little arrow. Let me see if I can get that to work right. We're going to make an arrow to show that we're saying those two sides are parallel. So triangle proportionality says if you draw this line segment EB inside of this triangle ADC and it touches two sides and is parallel to the third side, then you know something very interesting is true. Let's go ahead and write this out in a different way based on this diagram. If we know that segment EB is parallel, in this case, to side DC. Close this helper. Okay, then here's what we know. We know that segment AE, when set up as a ratio with the rest of that side, ED, so AE over ED, is equal to AB over BC. So take a look. When it says it divides the two sides it intersects proportionally, this side AD and this side AC, they are divided proportionally into these two smaller segments. Now one thing I'd like you to do, class, is circle this, this vertex A. This is the vertex that doesn't touch the parallel side to EB. And what's nice about this is this will help you set up your proportion. Notice that A is on top of our first one and it's on top of our second one. This may help you to keep from flipping those proportions or those ratios around. Some of you have been doing that every once in a while in class and you've been getting wrong answers because you haven't been setting up your ratios with the right thing on top and bottom. Alright, so we also know something else. We know that it creates similar triangles. Let's talk about this. So I'll put a little note here. Also, since angle, and let's call this angle AEB, since angle AEB is congruent to angle AEB is congruent to angle ADC, and angle ABE is congruent to angle ACD. Let's find out for a second, how do we know this? Well, class, you learned this in Integrative Math 1. When we have parallel lines, in this case EB and DC, and we cut across both of those lines with a transversal, then we know that these two angles are corresponding angles and they are congruent. These two angles, the two parallel lines are being cut by transversal AC. These two angles are parallel also because they are corresponding angles, and that's why we can say angle AEB, that's this one right here, is congruent to ADC, and ABE is congruent to ACD. And we know this again because of the corresponding corresponding angles rule. Now think about it. Since we know that, take a look at these two triangles. The original triangle and the smaller triangle, those two triangles are similar. Okay, so we can say then, since these angles are congruent, these angles are congruent, then by the AA theorem, I hate to actually run that into the other box. I'm going to fix that. So by the AA theorem, we know that these two triangles are similar. Let's go ahead and scroll up a little bit so we can actually draw that out. So let's kind of just sketch out these two triangles. Let's take a look at them. Let's just say this one is A, E, B. There's our smaller triangle, the one that's on top. Let's draw our bigger triangle. It doesn't matter whether they draw them perfectly right. This is our bigger triangle, A, D, C. You know what? A, D, C. There we go. So AEB and ADC. If you look at this one represents the smaller triangle. This one represents the bigger triangle. Since we know that this angle is congruent to this angle, and this angle is congruent to this angle, we know that these two triangles are similar by the AA theorem. And therefore we can write this triangle. Let's make sure we match these up. A is the one without any measurement. I can put that one first, doesn't matter. I know that A is going to, let's correct that. I know that A is going to correspond to the other A. That's a shared angle there. We're going to have similar. There's A. A matches up with A. E matches up with D. And B matches up with C. So I know that these two triangles are similar because this parallel line EB actually created a pair of corresponding angles which were congruent. And that's the triangle proportionality right here. This is just another property I'm showing you about parallel lines inside of triangles. So with this information, that AE over ED equals AB over BC, now we can solve some missing measurement problems. Take a look at a couple of them. I'm going to go ahead and do this first one. So here's our question. If BC is parallel to DE, what is the length of BD? So take a look at our triangle. We have line BC, and they're telling us that that is parallel to DE, so that we've got triangle proportionality now. What is the length of BD? Take a look. We don't know what BD is. We're going to use triangle proportionality to solve for it. Okay, first thing let's do is let's set up our proportions. Here is the vertex that is not touching the parallel side. So that one is going to always show up on top. So I'm going to write my triangle proportionality. AB over BD in this case. Notice class, different vertices is going to look different, but as long as you set it up correctly, we'll be able to solve it. AB over BD is equal to AC on the other side of the triangle over CE. This proportion will hold true because of the triangle proportionality rule. All right, let's plug in what we know. AB is 16. BD is our unknown. AC, oh, we got a problem here. We got a problem in AC. AC doesn't have a measurement, but look class, since AE is 30 and CD is 10, we can go ahead and solve this right now and say, I'll just put this in the margin over here. We know that AC is going to be equal to AE minus CE. So AC is equal to AE, which is 30, minus CE, which is 10. So AC is equal to 20. So there's our value here. I'm going to write that in. We figured that out. So AC is 20, CE is 10. Let's go ahead and do crossed product. So 16 times 10 is equal to 20x. 16 times 10 is 160, equals 20x. Divide both sides by 20 and you get 8 equals x. So our x value is 8. Here's how we're going to write this as a sentence. What is the length of BD? The length of BD is 8. And now we don't know what our unit of measure is, so we're going to write 8 units. There's our first solving for a missing side. Let's take a look at another one. If PQ is parallel to KJ, what is the length of SJ? So here's our PQ that is parallel to KJ. What is the length of SJ? All right. Let's take a look, class. Same as our last problem, we're going to need to know what SQ is before we have to figure out what SJ is. SJ is the whole side. We have to figure out what SQ is. Let's circle the vertex that is not part of our parallel lines, and let's write our proportion. So we're going to find SQ. So I'm going to put on here first, find SQ. And here we go. Here's our proportion. I'll start from S. SP over PK. SP over PK is equal to SQ over QJ. Notice again, this S showed up on the top of both of our proportions. All right, let's go ahead and plug in what we know. SP is 7. PK is 2. SQ is our unknown. QJ is 5. Let's go ahead and use cross product. 7 times 5 is equal to 2x. That means 35 is equal to 2x. Divide both sides by 2 and you get x equals 17.5. 17.5. So SQ is 17.5. So that means SJ, we have to add these two together. So to find SJ, I'll try a different color for this as you wrap this up. SJ is equal to SQ plus QJ. So SJ is equal to 17.5 plus 5. So SJ is equal to 22.5. So my final answer is going to be the length of SJ is 22.5. Again, we don't know what the unit of measure is, so it's 22.5 units. So there's your basic problem solving using triangle proportionality.